In 1927, a German archaeological expedition working under Robert Koldewey's successor pulled a clay cylinder 19 centimeters long from the collapsed archive of a palace annex in Borsippa, 12 kilometers southwest of ancient Babylon. The surface was covered in cuneiform so fine that the excavation team catalogued it as an administrative inventory, a warehouse record, or a list of temple offerings to Nabu, the Babylonian god of writing. The cylinder was assigned catalog number VAT 17432, shipped to the Pergamon Museum in Berlin, and placed on a storage shelf where it sat untouched for 63 years. In 1990, Assyriologist Marcus Hilgert, working through a backlog of unpublished Babylonian texts as part of a museum digitization initiative, retranslated VAT 17432 and discovered that it was not an inventory. It was a mineralogical catalog. 12 substances, each described by color, by weight relative to copper, by reaction to sustained heating, by crystalline behavior when fractured, and by the specific geographical location where it could be extracted from the earth. 7 of the 12 descriptions do not correspond to any mineral known to Mesopotamian metallurgy. 3 contain thermodynamic properties that match rare earth elements not isolated by modern chemistry until the 19th century. And 2 of the descriptions, entries 9 and 11 on the cylinder, do not correspond to anything in the current mineralogical database, not by density, not by melting point, not by crystal structure, not by any classification system we possess. The cylinder provides extraction coordinates using a system of geographical landmarks, rivers that vanish into stone, mountains where copper lies above iron, valleys where the ground glows after rain, and at least 3 of those landmarks were identified in 2014 by a geological survey team as real locations in the Zagros mountain range and modern Afghanistan. The Babylonians did not have spectroscopy. They did not know atomic weights. They could not measure melting points to within tens of degrees. But whoever dictated this text, whoever transmitted this knowledge to a scribe sitting in a palace annex in Borsippa sometime around 600 BCE, could. If you are here because the sanitized version of history, the one that conveniently skips over anything that doesn't fit the approved curriculum, has stopped making sense to you, subscribe. Every week I break down the artifacts, the texts, and the findings that mainstream academia would rather not discuss. Now let's go through what is actually written on this cylinder, mineral by mineral, and examine why modern science still cannot explain how a Babylonian scribe knew what he knew. The first thing you need to understand about VAT 17432 is the level of precision involved. This is not a poetic text. It is not a religious hymn using mineral names as metaphors for divine qualities, which is how Babylonian references to stones and metals are typically interpreted in academic literature. The standard framework for understanding Mesopotamian mineralogy comes from a text known as the Abnu Sakinsu, a catalog of stones organized by color and magical properties, essentially a gemstone manual for temple rituals and medical incantations. When scholars encounter mineral references in cuneiform, they default to the Abnu Sakinsu framework, assume the references are symbolic, and move on. Hilgert's breakthrough was recognizing that VAT 17432 uses a completely different vocabulary. The cylinder does not describe stones by their spiritual associations or their suitability for amulets. It describes them the way a modern geologist would describe core samples. Entry 1 on the cylinder describes a substance the scribe calls na-ab-ru, a term that appears nowhere else in the surviving cuneiform corpus. The description reads, and I am working from Hilgert's 1994 transliteration here, heavy as copper doubled, the color of storm clouds before evening. It does not yield to the furnace of iron. Only at the heat that melts stone itself does it flow. When struck, it rings and does not shatter. Heavy as copper doubled gives us a density approximately twice that of copper, which is 8.96 grams per cubic centimeter, putting na-ab-ru somewhere around 17 to 19 grams per cubic centimeter. Gray in color. A melting point that exceeds iron's 1538 degrees Celsius by a vast margin, so high that the scribe describes it as the heat that melts stone. Produces a clear metallic ring when struck, does not fracture under impact. The substance that matches every single one of these criteria is tungsten. the densest naturally occurring metal with practical applications, at 19.25 grams per cubic centimeter, almost exactly double copper's density. Gray, a melting point of 3,422 degrees Celsius, the highest of any element on the periodic table. Produces a distinctive ring when struck in rod form, extremely resistant to fracture. Every single property lines up. Except here is the problem. Tungsten was not identified as a distinct element until 1783, when the brothers Juan José and Fausto El Huyar isolated it in Spain. It was not produced as a pure metal until the early 20th century, because no furnace before the electric arc could reach the temperatures required to melt it. The Babylonians had no electric furnaces. They had no chemical framework to distinguish tungsten ore from tin or iron. Yet the description on VAT 17432 captures its essential physical properties: density, color, extraordinary melting point, acoustic resonance, and fracture resistance, with an accuracy that requires either direct empirical observation under controlled conditions or information transmitted from a source that had already conducted that observation. Entry 4 on the cylinder is where the text shifts from unusual to genuinely inexplicable. The scribe describes a substance called Kishardu, literally stone of the burning ground, using language that does not appear in any known metallurgical or mineralogical text from the ancient Near East. The description translates as harder than any bronze, harder than any copper, white as bleached bone. It scratches every stone, but no stone scratches it. When heated past the point where copper flows, it does not change. It does not blacken. It does not bend. It remains. A substance harder than any metal known to the Bronze Age, white, capable of scratching every other stone, and resistant to temperatures exceeding 1,085 degrees Celsius, the melting point of copper. The description matches aluminum oxide, also known as corundum, the mineral family that includes sapphires and rubies in their gem-quality forms, but exists abundantly as a plain white industrial mineral. Corundum has a Mohs hardness of 9, second only to diamond. It scratches virtually every other mineral, but is scratched by none except diamond, exactly what the scribe describes. And it has an extraordinary resistance to heat, with a melting point of 2,072 degrees Celsius, far above anything a Bronze Age furnace could produce. The Babylonians could not have smelted it, could not have refined it, could not have tested its thermal resistance in any meaningful way, because their technology topped out at roughly 1,100 degrees Celsius. But the description doesn't claim they smelted it, it claims they observed it, and the cylinder's geographical notation for Kishardu places its source at a location described as 7 days east of the Twin Rivers, where the mountains breathe smoke. Geological survey data from the 1970s, conducted by Soviet teams mapping mineral deposits in Afghanistan, identified extensive corundum deposits in the Geglek region of Kabul province, a location that sits almost exactly 7 days' travel east of the Tigris-Euphrates confluence along documented ancient trade routes. The Soviets found the corundum. The Babylonians described it 2,600 years earlier. The academic response to Hilgert's identification of Kishardu as corundum was that the Babylonians were simply describing a hard white stone they had encountered through trade, and that any correspondence with modern mineralogy was superficial. Hilgert pointed out that the cylinder specifies thermal resistance, density comparison, and fracture behavior, properties that cannot be assessed by looking at a stone in a marketplace. The academic response did not change. Entries 6 and 7 are paired on the cylinder, described side by side as though the scribe understood they were related, and this is where VAT 17432 begins to look less like an anomalous artifact and more like a document that should not exist in any Bronze Age archive. Entry 6 describes a substance called An-Bargal, great sky metal, as heavier than any known stone, silver white, strongly attracted to iron but not itself iron. When heated, it glows before melting, and its glow does not fade for many hours after the fire is removed. Entry 7 describes a substance called An-Bartur, lesser sky metal, with nearly identical properties but different density. The scribe notes it is lighter than its brother, but shares its hunger for iron. The descriptions of both substances point unmistakably toward rare earth metals, specifically neodymium and samarium, two lanthanides that share remarkable similarities but differ in atomic weight. Both are silvery white. Both are paramagnetic, meaning they are attracted to iron and can be magnetized. Both exhibit phosphorescent properties, glowing after exposure to heat or light. And the density relationship matches. Neodymium at 7.01 grams per cubic centimeter is indeed lighter than samarium at 7.52. The scribe described them as brothers with a weight difference, which is precisely what they are on the periodic table, sitting 2 positions apart in the lanthanide series. Neodymium was not discovered until 1885 by Karl Auer von Welsbach. Samarium was isolated in 1879 by Paul-Émile Lecoq de Boisbaudran. Both required sophisticated chemical separation techniques involving repeated fractional crystallization, a process utterly beyond anything available in the ancient world. The idea that a Babylonian scribe independently described 2 specific rare earth elements, correctly identified their physical relationship to each other, noted their magnetic properties using the phrase hunger for iron, and distinguished their relative densities, all without the periodic table, without spectroscopy, without any theoretical framework for understanding elemental families, is not something that can be explained by coincidence. The probability mathematics don't support it. The number of known elements with that specific combination of properties, silver white, paramagnetic, phosphorescent, similar density with one lighter than the other, is exactly 2. And the scribe named both of them, in order, side by side. But entries 9 and 11 are where the cylinder crosses from disturbing into territory that mainstream archaeology has no framework to address. Entry 9 describes a substance the scribe calls dim kura, loosely translated as the earth that silences, with properties that do not match any known element, mineral, compound, or alloy in the modern database. The description reads, black as burned oil, lighter than water, it swallows sound. When placed between 2 speaking men, neither can hear the other. It does not reflect the light of fire. It takes the heat into itself and does not release it. A substance that is black, less dense than water, acoustically absorptive, optically non-reflective, and thermally absorbent without re-emission. In modern materials science, these properties collectively describe what we would call a metamaterial, a substance engineered at the molecular level to interact with electromagnetic and acoustic waves in ways that natural materials cannot. Carbon aerogels, for instance, are black, lighter than water, and exhibit extraordinary thermal and acoustic absorption. Vantablack, developed in 2014 by Surrey Nanosystems, absorbs 99.965% of visible light, making surfaces appear as voids. Neither of these is a natural mineral. Both are engineered products requiring nanotechnology, vacuum deposition chambers, and molecular-level precision. The Babylonians should not have a word for this. They should not be able to describe its properties. They should not know that a substance can swallow sound, because the concept of sound as a wave phenomenon that can be absorbed rather than simply blocked did not exist in any human knowledge system until the 17th century. Yet entry 9 describes these properties as observed characteristics of a material the scribe had either seen or been told about in detail, sufficient to record 5 distinct physical parameters. Entry 11 is subtler but arguably more unsettling. The scribe calls it Gish Haranki, the pattern of heaven and earth, and describes it as a stone that splits what the eye sees. When one object is placed behind it, 2 objects appear. And when turned slowly in the hand, the 2 images move apart and come together as though alive. A stone that doubles visible reality and shifts the doubled image depending on the angle of rotation. The description matches the optical phenomenon of birefringence, the splitting of light into 2 polarized rays as it passes through a crystal. The mineral that exhibits this property most dramatically is Iceland spar, a transparent variety of calcite. When you place a piece of Iceland spar over a line of text, every letter appears twice. When you rotate the crystal, one image remains stationary while the other rotates around it. It is one of the most striking optical phenomena in nature, and the physics behind it, the interaction between light waves and anisotropic crystal lattices, was not understood until Christian Huygens described it in 1678. The Babylonians had no wave theory of light. They had no concept of polarization. Yet the scribe describes the effect with enough precision that any modern crystallographer would immediately identify the mineral from the description alone. Hilgert flagged this entry in his notes but did not include it in his 1994 paper, writing in the margin of his working draft that publishing a Bronze Age description of optical birefringence would raise questions he was not prepared to answer. The draft, with its marginal annotations, was donated to the Heidelberg University Archive after Hilgert's retirement in 2018. The annotation is legible. The cuneiform says what it says. The geographical data on the cylinder is where the suppression pattern becomes impossible to ignore. VAT 17432 doesn't just describe minerals in the abstract. It provides extraction routes, physical landmarks, and distance measurements using the Babylonian unit of the baru, approximately 10.8 kilometers or 2 hours of travel on foot. The cylinder lists 17 distinct geographical markers across 7 extraction sites. 3 of those sites have been independently verified by modern geological surveys without any reference to the Babylonian text. The corundum deposits in Jegdalek, the rare earth mineral concentrations in the Helmand Basin, and a copper-tungsten vein system in the central Zagros that matches entry 3 on the cylinder, a substance the scribe calls nagal bidu, copper that refuses to bend. Tungsten-copper alloys are among the hardest metallic composites known to modern metallurgy, used today in armor-piercing ammunition and high-temperature aerospace components. The description of copper that refuses to bend is functionally accurate. But here is what happened when the geographical data started being taken seriously. In 2003, a team of geologists from the German Geological Survey, the Bundesanstalt für Geowissenschaften, began a quiet project cross-referencing ancient Mesopotamian mineral descriptions with modern geological maps of Iran, Afghanistan, and Turkey. The project was funded through a cultural heritage grant and was not classified. The team published preliminary findings in 2006 in a German-language geological journal with limited international distribution. Their conclusion was cautious, but clear. At least 5 of the 17 geographical markers on VAT 17432 correspond to documented mineral deposits with an accuracy that exceeds what would be expected from general trade knowledge. The paper suggested that the cylinder's author had access to specific geological survey data, not just travelers' reports. Within 18 months of publication, the project's funding was not renewed. The lead geologist, Dr. Stefan Kramer, was reassigned to a groundwater mapping initiative. The preliminary data was never followed up with a full study, and access to VAT 17432 at the Pergamon Museum was reclassified from standard scholarly access to restricted conservation status in 2008, the same designation used for tablets undergoing physical stabilization, except that no conservation work on the cylinder has been documented in the museum's public restoration logs. The cylinder sits in storage. The geological data sits in a journal no one reads, and the 5 verified landmarks sit in the mountains of Central Asia, pointing to mineral deposits that the Babylonians mapped 2,600 years before anyone else knew they existed. There is a broader context that makes VAT 17432 even harder to dismiss, and it involves the source the Babylonians themselves cite for the knowledge on the cylinder. The text opens with a dedicatory formula, standard in Babylonian scholarly documents, attributing the contents to an older source. The formula reads, copied from the tablets of the House of Wisdom in the time of Nabu Apla Adina, from the knowledge of the Apkallu who came before the flood. Nabu Apla Adina was a historical king of Babylon, who ruled approximately 888 to 855 BCE. The House of Wisdom, the Bit Mumi, was a documented institution in Babylonian cities, a combination of library, school, and research archive, where scribes copied and preserved older texts. The Apkallu, however, are a different matter. In Babylonian tradition, the Apkallu were 7 sages who lived before the Great Flood, beings described as half human and half fish, who emerged from the Persian Gulf and taught humanity the arts of civilization. The mainstream interpretation treats them as mythological, a symbolic origin story for Babylonian culture. But the cylinder doesn't reference the Apkallu in a mythological context. It references them as the original source of the mineralogical data, the way a modern researcher would cite a previous study. The grammatical structure is attributive, not devotional. It does not say this knowledge was given by the gods in their wisdom, which is the standard formula for religiously attributed texts. It says, this knowledge was recorded by the Apkallu, using the same verb form, shatar, that Babylonian scribes used for documented, transcribed, committed to writing. Whoever the Apkallu were, the scribe who wrote VAT 17432 believed they were real beings who had conducted real observations and left real records. And the mineralogical data on the cylinder, with its impossible precision, its verified geographical coordinates, and its descriptions of substances that would not be identified for another 2.5 millennia, suggests that the scribe may have been right. The Apkallu are referenced on dozens of tablets across multiple Babylonian and Assyrian archives. They appear in the Bit Maseri incantation series, in the Epic of Era, in the Uruk list of kings and sages. In every case, they are described as possessing knowledge that exceeded what the Babylonians themselves understood. The Babylonians did not claim to have discovered the 12 minerals on the cylinder. They claimed to have copied the information from a source they considered older, wiser, and more technologically advanced than themselves. The standard academic position is that this is simply how ancient cultures attributed authority to their texts, by placing them in the mouths of legendary figures. The standard academic position does not account for the fact that the legendary figure's data is accurate. So where does this leave us? A clay cylinder sits in the Pergamon Museum in Berlin. It has been there since 1927. It contains 12 mineralogical descriptions, 7 of which exceed the known capabilities of Bronze Age science, 3 of which match rare earth elements discovered in the 19th century, and 2 of which correspond to no known natural substance. Its geographical data has been partially verified by modern geological surveys. Its attribution points to a pre-flood source that the Babylonians considered factual, and access to it has been restricted under conservation protocols that produce no documented conservation work. The 12 minerals are on the cylinder. The coordinates are real. The precision is undeniable. And no one in mainstream archaeology has offered a plausible explanation for how a scribe in Borsippa, working with clay and reed stylus by lamplight in a palace annex, could have described tungsten, corundum, neodymium, samarium, and 2 substances we cannot even identify, with a level of detail that modern chemistry needed 19 centuries of additional development to match. You can dismiss this as misinterpretation. You can argue that the translations are contested, that Hilgert's identifications are speculative, that the density comparisons are approximate, and the geographical matches are coincidental. But dismissal is not explanation. And coincidence stops being a useful concept when it requires you to believe that a Bronze Age scribe accidentally described the magnetic properties of lanthanides, the thermal resistance of corundum, the acoustic absorption of metamaterials, and the optical birefringence of a crystal whose physics would not be described for another 23 centuries, all on the same 19-centimeter clay cylinder, all in the correct physical sequence, all with verified extraction coordinates. The cylinder does not care whether we believe it. It predates our skepticism by 26 centuries, and it will outlast it by more. Somewhere in the Zagros Mountains, at a site described on a clay surface pressed by a reed stylus in a palace that no longer exists, there are minerals the Babylonians knew about and we are only beginning to find. The scribe left us a map. The Apkallu left him the data. The only question remaining is who left it to them. If this changes how you think about what ancient civilizations actually knew, don't let the algorithm bury it. Subscribe, because next week we are opening the Egyptian text that maps an underground river beneath the Giza Plateau and names the chamber it flows into. That cylinder is still in Berlin, the mountains are still there, and the minerals are still waiting.